So there's a fair amount of news this week. BASF, Pascal, getting in with weather, basically to improve weather with quantum computing. NSF, more funding, more senators, US senators kind of stepping in, introducing bills to improve quantum cybersecurity, or basically preventing quantum cybersecurity attacks on US soil. There's a BMW conference and also kind of like a Google Australian news. So I'll post that a little bit later. So if you'd like to, you can introduce yourself, Vinay.
Hey, sure. So, all right. Okay, let me just turn my camera. Yep. Okay. Cool. So, hi, I'm Vinay. I'm the CEO of AtomicLoops.com, and Atomic Loops is a software services company which caters to clients across the world. And currently, we are one of the very few companies which offer quantum computing as a consulting service. And we do help companies build end-to-end solutions. Like we start from the full tech stack, like we start from the front end, then we have quantum in between, then we have a Python backend. Then if some machine learning workloads are needed, we provide the full solution. And throughout that, we've seen some very interesting applications where people want to use quantum, and sometimes they do, and sometimes it does not work as planned. So I would just like to share some of these examples. I don't have a PPT, but I just wanted to share some applications of quantum machine learning and how I've seen these things being used across industries.
Awesome. Yeah, that's what a lot of us are here for, is basically learning more about the applications, especially this year and including next year as well. So that's cool that you have kind of hands-on with it.
Welcome, Vinay.
So, so if we kind of do a little briefer here, so I know Balaji and Brenda pretty well, so they've had me on discussion, and I've got to talk as far as like launching a quantum computing startup. So a lot of familiar faces. So Lorraine is a previous speaker as well, and she comes to pretty much all of these days. We do have Austin on, so he's kind of in government hospital. Ron does compilers. So Leonard is local to San Diego, and we know each other through some other kind of a small business development as well. And then Tim is on a lot. So Tim has a PhD in physics, and he's very helpful too. So do you guys have slides?
I have a slide. Just I will provide after the talk, and I'll use this slide. But Vinay told he can talk without slides, but if he has, that'll be good too.
Awesome. So I'm going to post some of your LinkedIn's, and then feel free, Balaji, anytime to talk about the Walt Disney Company. It's a huge company. It's Fortune 53 on the Fortune 500. So there's just, I think a lot of us kind of grew up watching either those cartoons or the music, or in your teens, basically exposed to entertainment business. Very, very interesting.
Yeah, I worked before. I mean, as a contractor, I'm not a full-time employee there. I worked a year ago. After that, I moved to Microsoft, and currently I finished that project. So as a contractor, I'm working for different companies as a software consultant. I work, the recent one is Microsoft. So I haven't updated in the LinkedIn. That's why I think it is showing the old posting. Yeah, of course, I worked in Orlando, but not in LA. So that was an interesting project about hotel management application development. So they have 3 hotels in LA and also Orlando. So that we are working on a content management area, so displaying different language settings. So that was interesting project, but it's not related to quantum, but my journey started in a different angle. So first let Vinay take the lead and start his talk, and then I will take from him.
Yeah, sure. And you could definitely relate it to basically how this, I've heard a lot of things as far as quantum machine learning still uses classical components for many parts, and kind of like if you have that perspective of basically where all this is going, and including quantum in the future too.
Hey, for sure. So, all right. Quickly, just setting the context, right? So, when we look at quantum machine learning, then it's basically a neural network that has to be optimized on a quantum hardware. And the ideal scenario is that these neural networks are very easy to be optimized on a quantum computer. And based on this optimization, it is very easy to find a quick solution on a quantum hardware. And the whole reason why people believe that is possible is because of quantum tunneling, where you can just find a quick solution to the gradient descent problem, which is for neural network optimization. And effectively, see, on classical systems, I'll give you an example. For example, we were working with a client called Swiggy. So that's like the DoorDash for India. And these guys handle 10 million orders every single day. Okay. And then what they wanted to do is, so these guys are delivery partners who pick up your food from a restaurant and deliver it to your home. So these guys wanted to optimize this by using some sort of AI. And through this AI, they wanted to, even if we can get a 10% improvement in how much distance this delivery partner has traveled, then it saves millions of miles driven overall, and that results in a lot of cost saving, plus of course a lot of carbon offset as well, because not everyone uses electric vehicles. So that's where we came in. And the initial approach was we tried to build a simple neural network, nothing quantum, a simple classical neural network. Let's just give them a machine learning model. Let's see how it trains from the usage every day. But then the problem that we saw is that we took the state of the art compute machine on AWS that was like using 16 GPUs at one time, and I believe like around 200 processor cores. And this machine is all that we could buy with money. And with this machine, even training the machine learning model used to take over 2 days, okay, for all of that data set. So then that was a very big problem, because these guys needed improvement on a daily basis. But even building this machine learning model, training it takes 2 days just to incorporate new data in the experiment. So that's when we try to optimize this. Like, okay, it's not possible if we can have a model that takes 2 days. So can we get it down? And how do we get it down? So that's when we started exploring quantum machine learning. That's when we saw PennyLane.ai. And through PennyLane.ai, we started using variational Eigensolvers. And through that, now we have built our own classical and quantum hybrid system. Like the neural network is built on a classical hardware, the data is accepted on a classical hardware, because the whole point is the data is somewhere on a hard disk, right? Because this data is in, let's say, an Excel form or a CSV form or a text file, and this data has to be processed. And currently, we don't have enough logic devices to accept data in a quantum environment. We can build circuits, we can optimize for these circuits, but accepting data in a quantum system is very difficult. So that's where we come in. We have built an end-to-end system where we try to optimize the neural network training as much as possible. And in this case, there are multiple scenarios. Like, we don't stop only at the gradient descent part, which is the most time consuming part. Like, from our experiment of 48 hours, this gradient descent only took 43 hours overall. So we try to optimize this using quantum hardware. And in terms
Smile,
of the
be like
hardware,
that.
You should be able to.
Big Dick Lou.
Okay, you should be able to go.
all right, cool. So yeah, in terms of the hardware, we have used Google's quantum device. Then we had some strategic tie-ups with IBM where they let us use their quantum hardware for some experiments. And on a more commercial basis, we use the D-Wave Leap system. It's a quantum annealer because that's what we need for ML optimization as of now. So yes, that's kind of an overview about how we use classical and quantum as a hybrid. And essentially what we have seen is these things scale like crazy. For example, if you look at a classical system and if you want to just run it with 2 times the same amount of data, like for example, another client that we were working on was Amul, which is a very big FMCG company in India. And they deal with a lot of consumable items like milk, then cheese, and a lot of dairy products. And the problem which they were having is quality control over the nation. And Amul has like 100 million customers every single day. So we are talking scale here. So with this scale, what they wanted to do is they wanted to ensure that we have proper quality control across their entire delivery chain. So that's where we built a few sensors which could integrate with their delivery pipelines. And these sensors communicated with our AWS servers. And once our AWS servers had enough data, then we fed it to quantum annealer again. And with that, we could get anomalies within that data. And using these anomalies, we could flag that this is a particular pipeline that is not working properly, or there is some quality control not happening over here, or the QA is not being done properly. So with that kind of, the reason why we went to a quantum approach was A, not because it is cool, but B, because we wanted to really save time. And these experiments were not possible before because we needed the output in less than a day with tremendous amount of data. So that's when we tried to go into the quantum route. And frankly, we are seeing some very good results. And I would still say that there are still a lot of problems that cannot be solved through a quantum computer. Like I've seen some of my clients try to address a lot of ML problems through a quantum annealer, but that's not the case. There are only specific pipelines, sections of the machine learning pipeline that can be optimized on a quantum hardware. It's not a one solution fits everything. So yes, that's kind of it. That's just my experience, some industrial applications. I'm happy to dive into detail. I apologize for not being prepared enough. I got to know about this a day back. So
yeah, and it's awesome that you're so hands-on with it. Obviously, a lot of us do want awesome quantum hardware that works on a variety of applications, but it's just not here yet. So
exactly
that's how that goes. So Virendra, did you have something?
Yes, I think Vinay and I have a long association going backwards in terms of our forum, and we have been doing sessions together. So Vinay, I'm not going to let you go. I know you are hardcore and you are thorough, and you will have something more for our audience here. So I'm just trying to bring in something very simple and where I'm sure you'll like to delve into those details. So one is the very first, to set it off, very simple question is, and I'm going back to your example on Swiggy, which you portrayed for us. So that solution and the neural network solution, is it the QML solution which you guys put together for them? Is it more a platform agnostic, which can be ported across other cloud platforms, or AWS is very closely tied to as it is right now? Of course, knowing your skills, your partners, and your company, I have no doubts we can take it to any platform. And I have a vested interest in saying that, because when I vouch for Oracle and Oracle Cloud and the way it's picking up in terms of all these areas now, putting this kind of solution onto Oracle platform, how easy, how difficult would that be? And how much kind of estimated time you think you will take? So it's a loaded question. Feel free to see whatever you can share in terms of your limitations from company or any confidentiality standpoint? And I have a question to follow as well as we dive into this.
All right, cool. So see, basically in the case of quantum computing, right, this is the biggest paradigm shift in terms of addressing a problem. Okay, so when we look at any problem and we try to map out the architecture, usually what we think is, so let's think of a simple machine learning problem. So the whole idea is you build a model, then you can take a model of any size, just give it to a GPU or a classical hardware, and then it will try to optimize this machine learning model and it will give you some output. But see, in the case of quantum computers, the whole problem is every circuit is related to a particular machine learning framework. Okay, so every problem has a different quantum circuit, and that's the basic building block. And from there, you try to optimize. So if we look at a QUBO problem on a D-Wave annealer, then this QUBO problem has to be formulated for every single machine learning model. Right. Even if we have different data sets, even if we have different architecture for the neural network or the QML system, and overall, this architecture has to be quantified for every new application. So it has been my goal as well to try to automate this as much as possible and provide quantum machine learning as a SaaS product. But as much as we all want to do it, it's not possible. So every solution has to be thought of from the scratch. Every ML model, every data set, we have to think about it from scratch. And frankly, we are pretty much cloud agnostic. So on
streaming on stream. Hey.
Okay.
Okay. So yeah, on the classical computing side, see, we are pretty much cloud agnostic. It doesn't matter where we are. It's all containerized, Docker. And so it just works along with D-Wave quantum annealer. So it starts experiments. It looks at the status of these experiments. Once these experiments are kind of completed, it takes the output, then it starts the classical pipeline. And from all of this, we have something that is a dashboard which the user can kind of understand at the end of the day. So yes, Virendra, short answer to your question is no, it cannot generalize as of now.
Okay, no, that's fine. And I think if I remember well, as you mentioned, 16 GPUs or something like that for the hardware you use for them.
Yeah.
Now, this was a GPU-based machine, and did you guys try, or even as an experiment, or you might be thinking, are you going for any ARMS-based computing for your servers, basically, because that even takes it a notch higher as compared to GPU-based machines? So that's why my question was coming from that angle.
Oh, okay. So see, in terms of ARM architecture, the whole problem that we are facing is, we are not having enough GPU compute. Like for example, when we look at ML compute and when we look at time critical ML compute, like these guys need to process terabytes of data within a day. Okay, and not just process, they need insights from it. So with that, frankly, we don't really care which architecture we use. If it's ARM based, if it's x86, as long as we are using the top performing hardware, we are okay.
Yeah, and that's why I was asking ARM, because ARM goes better than performing even against GPUs. That's what my understanding is, but I definitely wanted to hear that.
No, see, that is correct. It has a better, it has a better power rating per unit so let's think of it this way. See, if we can squeeze out, let's say, 10 units of processing per watt power given to the CPU, then in the case of ARMS, that is like 50-60 times what it is in case of classical hardware.
Correct.
All right, but see, that power efficiency is there, but if you look at the max output, that is still something which has to be improved. So
totally agree with you on that sense, that if we go back to our early years, few years back, when the multiple CPU hardware was thrown into picture for IT as well. So one of the major drawback which people face was, okay, you have now, instead of 10, 12, 64 CPU machine, but then we faced problem those years, early years, when people were finding it hard because CPUs were spending a lot of cycle to manage CPUs. So that piece had to be a trade-off. So where do you hit the right set and right combination to get the maximum throughput, which is very, very kind of required in this case, as you said, the insights within the day, a terabyte of data has to be processed. So let's dive a bit more into that, if you allow me. What kind of variables were spotted? And give us as much as you want to. Again, it's your choice. And what kind of variables really helped in bringing about the optimization you were looking for? Give us a little more meat on that.
All right, sure. So see, some of this is, so
and you can talk
I'll
in
not answer it
network
completely.
Terminology as well. Yeah, feel free to jump into.
See, in terms of the business use case, right? So Swiggy as a delivery partner. So if we look at just one city, okay, in this one city, they have a few nodes. Okay, let's consider like they have 50 odd nodes in a city. And what they want to do is, their whole idea is they want to transfer their delivery partners in such a way that it caters to the most number of people. Okay, and these nodes are spread across the city, and their delivery partners have instructions to just go to a node, wait over there, and once you get an order on your phone, just go to that restaurant, pick it and deliver. So the variable which we handled was the location of all of these nodes, then the distance from the average distance of an order from these nodes, and then we tried to get that down. Like, so what we understood is in the afternoon, there was some snacks outlets near a few nodes. And at that time, moving the delivery fleet to these snack centers was more optimized. And towards the afternoon time, we could move them to the lunch areas. And all of this insight was never hard-coded on the system. This is something which the neural network came up with of course, repeated data. So see, sometimes these important learnings are something which we miss by building a classical system. But with a full-fledged quantum machine learning system, these things are something which are available by default because you get advanced insights on the data set. And yes, till from the time we have started, we have saved over 70,000 miles of travel throughout these delivery locations, and we are on track to do a lot more. Our goal is to save 1 million miles by the end of this year overall traveled. Let's see.
So could I say that, to simplify in a very simplified fashion what you just said, it's that this model is more amenable to processing common sense also, because it's insights is generating a lot of common sense as well, that your people now should be closer to lunch area or dinner area or other areas in terms of delivery fees location. That's one piece of the story. And the second piece is where I want to have a bit of more understanding how far you were able to leverage the classical traveling salesman problem knowledge into this solution. How much of it or nothing of it, or how much was that part of the implementation? Because that's a very classical problem and people still try to solve that through various algorithms every day. So that's where I want to basically have your insight.
For sure. So if we look at the basic of a classical traveling salesman problem, then the whole idea is we have, let's say, 10 cities. The salesman has to travel all 10 cities and minimizing the travel.
Yeah.
But see, in this case, what we do is, see, we have nodes. So essentially, it might look similar to a traveling salesman problem, but ultimately what we want to do is, I want these delivery partners to visit as few nodes as possible. I don't want them to cover all of the nodes. Okay, because then it defies the purpose, because we have different people in different locations to do that. So this is like multiple salesman problem where we have multiple salesmen at multiple cities trying to sell the same thing. So I don't think there is a lot of correlation between.
Yeah, you hit it. Thank you.
And this is awesome discussion.
Over to you, Kevin, back.
Yeah, I'm learning a lot, that's for sure.